So here's a weird thought experiment. Let's say there's an alien civilization living on a planet just 4 light years away, orbiting Alpha Centauri. Close, right? Practically our neighbor on a cosmic scale. And let's say they're technologically advanced. Way more advanced than us, actually. They've been broadcasting signals into space for the last 10,000 years, trying to say hello to anyone who'll listen. Here's the weird part. We might never pick it up. Not because our equipment isn't good enough. Not because they're too far away, but because of something baked into the actual physics of how information travels through the universe. Turns out, the way we've been thinking about detecting aliens might be built on a broken assumption. And once you see the assumption, you can't unsee it. Let's start with the simple case. When most people picture detecting an alien signal, they picture something like the movie Contact. A radio telescope pointed at the sky, silently listening, until one day, beep, beep, beep. A repeating pattern. A prime number sequence, something clearly not random. That's how SETI has worked since the 1960s, more or less. Point big radio dishes at nearby stars, listen for narrowband radio signals, the kind that don't occur naturally, and hope you catch something in the tiny slice of time and frequency you happen to be listening. Simple enough. A signal is a signal, right? If it's out there, and it's strong enough, and we're listening at the right time, we should eventually hear it. Here's where it gets complicated. Radio waves are classical information. They spread out. They weaken with distance. Inverse square law, the same reason a light bulb looks dimmer the farther you stand from it. A signal broadcast omnidirectionally from 4 light years away is, by the time it reaches us, spread across a sphere with a surface area of roughly 1.4 times 10 to the 33rd square meters. Our telescope dish catches maybe a few hundred square meters of that sphere. Do the math, and you're catching something like 1 part in 10 to the 30th of the original signal. That's not a signal anymore. That's noise wearing a costume. So any civilization that actually wants to be heard across interstellar distances has 2 options. Option 1, broadcast so much raw power that even a whisper-thin sliver reaches us intact, which costs an absurd amount of energy, possibly more energy than a civilization can reasonably spare. Option 2, don't broadcast omnidirectionally at all. Aim a tight, narrow beam directly at a target star system, like pointing a laser instead of turning on a light bulb. But option 2 has its own problem. If you're aiming a beam at us, you have to already know we're here, and know where to aim, and know when. Because stars move, planets move, and a narrow beam that's a fraction of a degree off just sails past us into empty space forever. This is sometimes called the SETI paradox. The more efficient and realistic a civilization's communication method is, the less likely it is to accidentally reach us. And the methods that would reach us easily are the ones that are least efficient, meaning less likely to actually be used for very long. So already, before we even get to quantum mechanics, classical radio signals are a much narrower target than the sci-fi version suggests. Now here's the insight, the part that reframes everything. Let's say a civilization is smart enough to realize broadcasting is wildly inefficient. What would they use instead? Increasingly, physicists who think about this seriously point to quantum communication, and specifically, quantum entanglement. You've probably heard entanglement described as spooky action at a distance. 2 particles get linked in such a way that measuring one instantly correlates with the state of the other, no matter how far apart they are. Now, important caveat before anyone gets excited. Entanglement cannot be used to send information faster than light. That's not a technology limitation. That's a hard rule of physics, verified endlessly, no exceptions found. So entanglement alone isn't some magic loophole for faster-than-light alien chatter. But here's the thing, entanglement is uniquely good at. It lets you build communication channels that are, by their nature, essentially undetectable to anyone except the intended receiver. Quantum information doesn't leak the way classical radio waves do. There's no broad, weakening sphere of signal spreading in every direction for anyone to eavesdrop on. A civilization using quantum channels, say entangled photon pairs sent through carefully aimed quantum links, wouldn't create the kind of ambient, detectable noise that a Dyson sphere or radio broadcast would. Think of it like the difference between shouting across a canyon and passing a note directly into someone's hand. The canyon shout can be picked up by anyone standing anywhere in the canyon. The note can only be read by the person it's physically placed with. This is sometimes floated as one possible answer to the Fermi paradox, the famous "where is everybody" question. If advanced civilizations quickly figure out that quantum-based, targeted communication is dramatically more efficient and more secure than blasting radio waves into the void, then the natural endpoint of technological maturity might be quietness, not loudness. Not because they're hiding, just because shouting stopped making sense once you had a better tool. And here's the number that makes this sting a little. Humanity has been broadcasting detectable radio signals for less than 130 years. If the typical lifespan of a loud radio broadcasting phase for a civilization is only a few centuries before it transitions to quieter, more efficient methods, which is a real hypothesis in the Fermi paradox literature, then the odds of two civilizations both being in their loud phase at the same time, close enough to hear each other, gets vanishingly small. We might simply be shouting into a canyon at exactly the wrong 10 minutes in cosmic history. Caveat time, because this isn't fully settled. A few honest complications. First, we don't actually know if quantum communication over interstellar distances is even physically achievable at scale. Maintaining entanglement over 4 light-years, let alone thousands, runs into decoherence problems that no one has solved even theoretically, let alone in practice. It's a reasonable extrapolation of trends, not a proven engineering path. Second, this whole argument assumes advanced civilizations behave rationally and converge on efficiency. But that's an assumption, not a law. Maybe some civilizations keep broadcasting anyway, for cultural or historical reasons, the same way humans still use fireworks despite having far more efficient ways to celebrate. And third, maybe the most important caveat, even if this theory is right, it doesn't mean detection is impossible. It just changes what we should be looking for. Some researchers now argue SETI should widen its search beyond radio signals entirely, toward technosignatures like atmospheric chemistry, waste heat, or megastructure light curves. Passive evidence of existence, rather than an intentional hello. So where does that leave us? Maybe the silence out there isn't evidence of emptiness. Maybe it's evidence that we're listening for shouting in a universe that grew out of shouting a long time ago. Or maybe there's just nobody out there. Honestly, we don't know. Which, if you think about it, is a pretty unsatisfying answer for a video that promised you quantum aliens. I did say I'd explain the quantum reason we might never detect them. I didn't say I'd explain the reason there's anyone to detect at all.